So what I'm going to tell you about in the next 20 minutes or so is really a new view of single neuron computation that has emerged from our work over the last years. And what's at the center of this is basically that we observe that the process of Q integration is really a central computational principle of cortex. So whether you take a neuron that sits in the early visual cortex that needs to integrate information from different receptive fields, or whether you think about a neuron that sits more higher up in multisensor areas that needs to integrate information from multiple modalities, sort of this principle of accumulating information and not just summing it up as it's traditionally thought is really central. And in the following, I want to present to you our theory of how we think about single neurons do this, and in particular, how single neurons can do this with the help of conductance-based synapses. But for this, first, we're going to take we're going to make an observation, and we're going to start with thinking a bit about Bayes optimal inference, where the problem is that you have some prior expectation about a quantity of interest, for example, the angle of an oriented edge, and then you have different measurements of the actual angle. And now, typically, these estimates are unreliable, which means that they have some uncertainty attached. So we will make use of the tools of probability theory, meaning that we will represent each of these, our prior expectations, and these measurements as probability distributions. And now, once we have specified these distributions with their associated quantities, like the mean and the variance, or how we will refer to it as the precision, then we can actually just turn the Bayesian crank and we can compute what the posterior distribution will look like. So this posterior distribution now really integrates information from all these different sources, from the prior and from the different measurements. And what you can see is that the resulting mean of this posterior distribution is a weighted average of the means of the original distributions. And these weighting factors are indeed the precisions. The precision simultaneously of the resulting distribution, so of the posterior, is really just the sum of the precision of the individual distributions. So this means that the mean, or that the distribution really represents a compromise in the sense that the mean sort of finds a middle ground between the means of the original distribution, but it becomes sharper, meaning that the uncertainty about the quantity of interest is reduced. Now we're going to have a look at something that is seemingly unrelated, namely the stationary state of bidirectional voltage dynamics in multi-compartment neuron models. So here we assume we have a cortical neuron model that we have, which we just model with 4 compartments, the somatic compartment, and then 3 dendritic compartments, where the apical compartment receives mainly top-down input and the basal compartments receive bottom-up input. And now what we can do is we can actually compute for a simple neuron model, we can compute the stationary state, meaning the membrane potential that we expect will be represented in the somatic compartment for fixed input after some time. And here we see that this membrane potential is actually a weighted linear combination of the dendritic potentials. And the weighting factors are the conductances that are generated on the dendrites. Now, these typically include the Lie conductances, for example, but also the synaptically generated conductances. At the same time, the total conductance that is represented in the soma is the sum of these conductances. Now, of course, now if you compare the right-hand side and the left-hand side, then you can immediately see that it would be meaningful to identify the mean of a distribution with the membrane potential, which we also refer to as an opinion, because this whole framework is inspired by probabilistic opinion pooling. And at the same time, you can identify the conductance that's generated with the precision or the inverse variance. And now basically what we claim is that every dendritic compartment has the potential to represent probability distributions. Here, the prior distribution and the likelihoods. And then the somatic compartment computes the posterior distribution. To make this a bit more formal, what we can do is we can actually look at how this posterior is generated from the prior and the likelihoods. And for the particular example that we've chosen here, namely for Gaussian distributions, you will see that the posterior is really just a product of all of these distributions. And for a neuron, we can now formalize this. So we can write down the probability distribution that is represented in the soma, given all the dendritic distributions and the prior. And because all of these are Gaussian, the posterior is also Gaussian, where now you explicitly see that the width of this distribution is determined by the inverse width of this distribution is determined by the total conductance on the soma. And the mean of this distribution is determined by the weighted linear combination of the dendritic potentials. Once we have this distribution, we can basically, we can hypothesize that the member potential dynamics actually realize noisy gradient descent on this distribution. And then after some math, what you will get out is this differential equation, stochastic differential equation describing the membrane potential of the soma. And here you see that it's actually looking quite familiar in terms of what you traditionally think of are multi-compartment neural models with conductance-based synapses. Now we have this additional noise here introduced because this allows us really to represent the two moments of the posterior, right? So the expected or the average member potential represents these reliability weighted opinions, while the variance of the member potential represents the inverse variance or the precision. Now, within this framework, we not only just derive neuron dynamics, but we can also derive the weight dynamics. And for this weight dynamics, we can assume that basically we have some distribution that is represented in the soma. This is the red distribution, but we actually would like to have, represent the distribution P star. And then we can optimize the synaptic weights that project to the different compartments by performing stochastic gradient descent on the log likelihood, on the log posterior in this case. So we pick a sample from the target distribution, we plug it into our posterior distribution, and then we do gradient descent on this. And what we will see is that if you actually compute this, that there are two terms that determine this, the change in synaptic weights. And one is more related to the mean of the distribution, and one is of the width of the distribution. Now, looking at this in detail, you will see that this mean term actually looks quite familiar. So it has the target potential, and it has the potential that is currently realized in the neuron. So this very much looks like the delta rule, for example, or like other rules that are based on predicting somatic activity from the dendritic potential, for example. Now, the second term here is really arising because we're considering conductance-based neural models. And this basically measures how far the somatic potential is from the reversal potentials. And because the reversal potential, this E bar, will be always between the excitatory and inhibitory potential, this has different signs depending on whether we consider an excitatory or inhibitory synapse. Now, the second term in this plasticity rule is really related to learning to match the total conductance generated in the neuron to the variance of the teacher distribution. Because remember, we do not only want to match the mean of the distribution, but we really want to match the full target distribution. And one particular prediction that comes out of this model is that actually the synaptic plasticity modifies excitatory and inhibitory synapses in approximately opposite directions to match the mean of the target distribution. But it matches them in opposite direction to match the in identical directions, sorry, to match the variance. And this is something that could potentially be experimentally investigated. Now, to illustrate this plasticity rule a bit better, what we will do is we will consider a simple setup where we have the single neuron receiving input on two dendritic compartments, where one input fluctuates more strongly than the other input. This will be important later. And then additionally, we have the target, or we have a teacher. Now, what you can see here is that initially the somatic potential, which is the red trace, will not match to the trace that is determined by the teacher. But then after we've applied the plasticity that I described on the previous slide, you would see that actually both the mean and the variance of the somatic potential match to the teacher. Now, importantly, what also happened is that the synapses that are projected, the synapses that are arriving on this neuron from the modality which is less reliable, meaning that contains more noise, will be smaller than the synapses arriving from the other projection. And now this is just a sketch, but we can actually simulate this because we have the equations describing the neuron dynamics and the weight dynamics. And now here at the bottom, we will have the fluctuating input rates It's very hard to see, but actually under the blue line, there's a black line, which is the true input. And then we add on top of this true input, we add noise of different amplitudes, and the noise for the green modality is larger. Then what we can do is we can look at the membrane potential of the soma before the teacher is present. This is the dotted line, and correspondingly the dotted distribution on the right-hand side. And then you see after the teacher is present. So basically this means we set the learning rate unequal to 0. What will happen is that the mean of this distribution increases quite quickly to match the teacher mean, but then over time also the width of this distribution will match. And if we look at the joint weights that are arriving from on these both dendritic compartments, you will see that they decrease because the teacher distribution is actually wider than the initial distribution of the neuron. And this is a bit hard to see, so we also plot the relative weight. You will see that over time, there's really a difference developing in the total synaptic strength arriving from the modality which has more noise, the green synaptic weights, and those arising from the modality which has less noise, the blue weights. Now, this was already a bit more than just a sketch, but of course, it's maybe more interesting to look at an actual task. And here we've considered a typical experiment where a rat has to distinguish the orientation of a grating into basically horizontal or vertical, meaning more or less than 45 degrees. And this is a multimodal task. So these rats can either touch the grating with their whiskers or they can look at it. And then during the experiment, you can regulate whether they can only touch it, only look at it, or can do both. Now we've tried to reproduce this experiment with an extremely simple setup, to be honest, where we just have some true orientation, and then we generate modality-specific orientations from this true orientation by adding Gaussian noise with 0 mean. And what we will keep throughout this experiment is that the tactile modality, so the green pathway, will have more noise than the blue pathway, the visual modality. Now we generate from the true orientation these two Q orientations and feed these into two populations of feature detectors, which then project to two output neurons, which are modeled as I've described previously. One of them is trained to detect orientations larger than 45 degrees, so having a firing rate for orientations larger than 45 degrees, and one is trained to have low firing rates for orientations larger than 45 degrees and high firing rates for orientations lower than 45 degrees. Now we will just look at the performance, which is basically how well does it classify an orientation into the correct category, vertical or horizontal. And here we plot the average loss for different conditions. The first condition is really the ideal observer. This is the map. And then we plot the performance of our neural model after learning. And what you can see is that actually the loss between these two approaches is almost identical, meaning that our neural model has not only learned to match some target, but it has also learned to weigh these both inputs, so these both cues it receives appropriately to model the ideal observer. And the ideal observer from the beginning has information about how reliable each of these inputs are, whereas our neuron model actually needs to learn it from the presentation. And of course, this average loss is now smaller than the loss you would get by either considering both cues equally reliable, so weighting both each equally, or only considering one modality as input. Furthermore, what we can do is we can actually now compute the psychophysical curve for our trained model, meaning the proportion of stimuli that were classified as vertical as a function of the stimulus orientation. Now, for a perfect classifier, this would just be a step function, right? It would be 0 for orientations smaller than 45 degrees, and it would be 1 for orientations larger than 45 degrees. But because there's some noise and unreliability in general involved in detection of these cues, what we'll see are these sigmoidal curves. And now quite intuitively, you see that the step is sharper for the more reliable modality. So for the modality that has less noise, the model makes better predictions, right? Approximates more the step function. Now, of course, we can also present cues for both modalities at the same time. And what we'll see is that the slope of the psychophysical curve increases. And this is actually quite comparable to what people find in experiments where they measure how rats perform in this task. So how well, what the proportion of gratings called vertical is as a function of the angle. Now, furthermore, our model can allows us to make a bit more interesting experiments. For example, it allows us to model cross-model suppression, a quite interesting phenomenon, I think. And here in this case, so what I've shown you before, the cues were generated by the same ground truth orientation. But now what we will consider is a situation where you have two stimuli, one for the tactile and one for the visual modality, which are actually not aligned. In our specific case that we will consider here, the visual stimulus is more aligned with the neuron's preferred feature, which is about 90 degrees, than the tactile stimulus. But otherwise, the setup is the same before. So now we can plot the firing rate of the neuron that detects orientations larger than 45 degrees as a function of the stimulus intensity. And now, not surprisingly, because both of these stimuli are actually quite aligned with the preferred stimulus, you will observe an increase in the firing rate as you increase the stimulus intensity. But now something interesting happens when we actually present both stimuli at the same time. What you will see is this. So for low stimulus intensities, you actually observe that there's a firing rate increase compared to the unimodal conditions. However, for high stimulus intensities, you observe that the firing rate is much smaller in the bimodal condition than in the strongest unimodal condition. And this phenomenon is generally known as cross-model suppression. And incidentally, this is also what is observed in experiments, where monkeys were asked to do this multimodal integration. Now, because we have this model, and we have really a mechanistic description of how neuron dynamics and synaptic weights evolve, we can make predictions. And one of the predictions here is that this amount of cross-modal suppression really depends on how reliable each of these cues is. So for example, if in this experiment we would make the tactile cue much more reliable, or equivalently the visual cue much less reliable, what we would observe is, or what we would expect, is that the red curves actually moves towards the green curve. Because the neurons listens more to one of the modalities, namely to the one that is more reliable, we would predict this also to happen in experiments. And with this, I would already like to come to an end. I've shown you that neuron models with conductance-based synapses quite naturally implement the computations required for probabilistic Q integration. I've demonstrated that our plasticity rule doesn't only match the somatic potential, but it really matches the distribution of somatic potentials, and that it also learns to weigh pathways according to their reliability. Afterwards, I demonstrated that the model, when trained in a multisensory Q integration task, reproduces quite a few behavioral and neural experimental data sets. Unfortunately, this got a bit short due to time constraints, but I hope you can read more in the paper. And where we would like to go next is really make, based on this direct connection between the normative and the mechanistic descriptions, very detailed predictions or post-diction for specific experimental setups, like I've already shown a bit here. Now, of course, for everyone who has worked before with conductance-based neuron models, integrating these can be quite tricky. So we believe that especially analog neuromorphic systems, which naturally exploit the device physics to implement these kinds of equations, would present a very fitting substrate. Thanks.